Right, thank you everyone for joining. We'll make a start. My name is Mark Anis. Nice to meet you all. I'm part of the Young Members Committee at the TWI. We've got an excellent session planned for you today. We're going to talk about an introduction to NDT of Welds. Briefly, just a slide on the YMC first, what we are. So it's a group of young engineers. It's part of the TWI. We've got a passion for welding, for engineering. We want to take this knowledge and transfer it all across the industry. So there's a lot of networking. We've got people from all different companies. The intent is to promote this network of young engineers with a view to develop their careers. Because the TWI, because the YMC kind of has a voice within the TWI, so we can bring those needs to the TWI and let them know of all your views and perspectives and opinions. And we support the local branches as well for the TWI, so all across the UK. But if you're interested, yeah, I've got a slide at the end to register for interest, whether it's a membership with the TWI or in the Young Members Committee. But for now, we'll dive straight into it. So we've got an excellent session planned for you today about NDT of Welds. So mainly focusing on surface inspection methods. So that's visual, LPI, MPI, radiography, UT. And we've got Alan Denny speaking to us. He's a man of a wealth of experience, over 50 years. He's a corrosion engineer, welding engineer. He worked at Arup, at Wood Group. He's for SIPEM. He's done loads of stuff. I'm really excited to hear what he has to say today. He's currently a volunteer with the TWI, even after retiring. He's the editor for the Welding and Joining Matters, issued by the TWI as well. And he currently offers consultancy services and in appearing, supporting in arbitration and court cases as well. So an excellent session planned. Thanks for attending. We'll dive straight into it. Alan, one more thing, questions. If you have any questions, please put them in the chat function. I will relay them to Alan at the end, and any that we're not able to cover, we'll try and send responses to those afterwards. This presentation is being recorded, and we will share this in due time after the event. And if we have Alan's permission, the slides will be shared as well. All right, over to you, Alan.
Okay, thank you, Mark. Thank you for the introduction. Okay, I'm Alan Denny. I'm a metallurgist, a welding engineer, and a corrosion engineer, as Mark said. This presentation is really, well, it is what it says it is. It's an introduction to NDT of Welds. And I'm not an NDT engineer. I've had to learn all of this the hard way through some challenging experience through the industry, how NDT is used, how it relates to Welds, and how it fits in a whole scheme of quality control, quality assurance, and inspection technology. So I hope this will be interesting to you and not either too superficial or too heavy. But there's a fair amount of detail. So the methods I'm talking about are, well, I'm going to be talking about MPI and liquid penetrant inspection. I'll mention visual inspection in passing, but these are all good, it's working. Surface, these are to inspect for surface or surface breaking defects. So they're only telling you about what's on the surface. If we want to look at the volume of the weld metal, then we're into ultrasonic testing or radiography. And I'm going to talk about those. And I'm also going to talk a little bit about that bit of automatic ultrasonic testing that I know about from my experience. So they're to detect embedded defects. So these families of techniques are complementary. And there are lots and lots of methods of non-destructive testing. This is not an encyclopedic presentation. I mean, a very important one is eddy current, which I don't really touch on here. But there's also acoustic emission, flux leakage methods, and many other techniques. And I'm sure Mark, with his involvement in flexible pipes, will have experience of many other variants of inspection, but I'm just keeping it to the basics that everybody needs to know about when it comes to welds. Starting with MPI. MPI, well, MPI is for steels. It needs material that can be magnetized. It finds surface breaking defects only, and when it's in action, you'll see somebody doing something like that. So what's the method? Well, the method is, first of all, you put a white coating on the piece of steel and it's applied to the area which is under inspection. And in this case, it's a circumferential weld in a pipe. So that's why it's only in that band. That's the band where the weld is. And then you spray on an ink of fine iron filings in a carrier fluid. Now, I guess if you don't have direct experience of MPI as an inspection method, but you will have played with iron filings and magnets. So, and it's the same principle, the same technique. You're applying the ink, it's in a carrier fluid, and you have to simultaneously locally magnetize the component. And what you see is something like that. So there we've got a weld. There's a weld there in a nodal joint, and you've got a very, if I can use the word, nice crack at the toe of the weld, probably a heat-affected zone hydrogen crack, I would guess, which shows up very nicely with MPI against the white background. Now, alternatively, you can use fluorescent coated particles, and then indications have to be shown under fluorescent light. So that's a crane hook that's been examined, and then under fluorescent light you're seeing the indication there. And those weren't my photographs. These are my photographs. This is a pipeline, and it's actually a pipeline girth weld which has been excavated. And you can see the excavation on the left, and you can see the lamp, the UV lamp being used to inspect the weld. And what we're seeing is a lamination. Now, that lamination was actually detected, first of all, by automatic ultrasonic testing, but then we've excavated and we've found this lamination in the steel plate that has been used to make the pipe. Shows up as that brilliant green line. The principle is, well, if you've got a magnetized piece without discontinuities, then you establish a magnetic field and you get those magnetic field lines. But if you've got a crack, then you get something called flux leakage. And you get a local north-south magnetic poles formed, and you've got the magnetic particles there piling up on the surface, which are attracted to the indication there, to the defect there. How's this done? Well, the most popular method, the best method probably, is to use electromagnetic yokes. I mean, if we're talking about inspection of fabricated items, there are other ways of magnetizing components, engineering components like shafts and so on in a factory setting, but you know, in a production line setting. But here we're using an electromagnetic yoke. You've got a soft iron core. You've got those windings, cable windings, which generate, we turn that into an electromagnet, and that induces the magnetic field in the piece. And you can see there the crack marked and the flux leakage. And magnetic field strength is normally required to be between, I think this is old language, 30 and 50 Ørsted. I forget what modern units are, but anyway, in my day it was always Ørsted. So 30 and 50 Ørsted. And that yoke, look at it, it's got these jointed sections, and that's so that you can get into complex geometry positions, and you've just flexed those joints. You have to calibrate it, and that's generally, in the code you're working to, you have to be able to lift a load of a certain weight. We've already mentioned the white background paint, which is applied. So you've calibrated the equipment, you confirm that it will lift that weight. It can therefore develop the adequate field strength. You put the white paint on. And you might use actually, you can have two. I've talked about an ink, which is a liquid medium, but there's a limit to the temperature that you can use that because it will fume. So if you're looking at a piece which is hot, then you have to use dry medium, which is just powder, loose powder. Now that's obviously more difficult to work with, but it has a much higher temperature limit in practice. And you don't know where those cracks or defects occur, and so you do it in this crisscross fashion, as shown there, and that ensures that whatever the orientation of the defect, you will be cutting, the defect will cut the lines of force and will create that local magnetic field. So what are the benefits, advantages, limitations of MPI? Well, it's relatively easy training. The limitation is it's only used with ferromagnetic materials, of course. It's very sensitive, but it can only detect surface defects. You can actually use it with lightly coated pieces, but generally best applied to bare pieces. And the piece shape can be a limitation, but you try and avoid that by choosing your yoke to suit and by bending your yoke to suit. The interpretation is very simple. So it's an excellent low-cost inspection method for steels for surface breaking defects. And there are acceptance levels because you will pick up all kinds of little indications on the surface which are caused by debris and so on. So there are acceptance levels, and they're defined in your application code or standard for the particular piece. So it's different if it's a pipeline. It's different if it's a pipe from a pressure vessel. It's different if it's a pipeline done to American standards compared with the Norwegian DNV standards, which are widely used, or the British standards, which are basically EN, European standards. Moving on, liquid penetrant inspection. And you start by spraying. It's very simple. You start with a series of aerosols and an awful lot of scrap cloths. So you spray on this liquid penetrant, normally a dye. It's got high fluidity. It's sprayed onto the surface of the part and it's left to soak, left for maybe 5 or 10 minutes. Again, that's defined in the application standard. The excess liquid is then removed from the surface so that you can no longer see any dye at all. But what's happened is that dye has penetrated down into the defect, the crack that you see here, drawn in by capillary action. And then you spray on a developer, and that's basically a chalk powder in a carrier medium. So this is your next aerosol. Actually, it's your third aerosol. You've had your dye, you've had your cleaner, and now you've got your developer. And you spray that on, and that draws the penetrant out of the defect, and it can be seen on the surface. And that's the sort of thing that you see. And the penetrants can be either brightly coloured or they can be a fluorescent dye, and then you look at it under black light. So that's where you're using a fluorescent dye with ultraviolet light. So what are the benefits of dye penetrant? Well, or liquid penetrant? Well, it can be applied to all materials. The temperature range is again limited. It's only a surface detection method, as we've said multiple times. It's very simple procedure. It's very simple interpretation. You have to make sure that the surfaces are clean. It does require very good cleaning, and it also requires a fairly good surface condition. It's not limited by shape, so it has benefit over MPI in that respect. The equipment is truly inexpensive. It's 3 aerosols and a lot of rags, but I've already mentioned the issue of surface finish. Of course, with MPI and with liquid penetrant, it's carried out in accordance with industry specifications. I'll give you a list of those at the end. And again, there are acceptance criteria, but they're defined in the application code. So again, it's different for pipelines to one standard or another, pressure vessels, nuclear components, and so on. Or sometimes the client spec will override all of those and set a different set of acceptance levels, whether it's 1 millimeters that's acceptable or 6 millimeters. Moving on. Talking about radiography. So there's a fairly typical looking radiograph, not a very good image. But the principle is, I don't know whether you're seeing that image superimposed over the top there. Anyway, it's gone. Okay, you've got a source of radiation. Okay, and that beam is that white beam that you see there. You've got your weld there, which is shown in the darker blue in your piece of steel, which is shown in the light blue. And somewhere there, you've got a cavity, or you've got a defect or whatever. So you're shining the radiation on the piece, and then you have on the other side, I'm going to talk about film radiography basically, but you've got a piece of film there. But either side of the film, which is shown in green, you've got intensifying screens, which actually are fluorescent, which fluoresce and create secondary radiation, if you like, which helps to intensify the image on the film. But what you've also got is you've got bits, X-ray, reflected X-rays or reflected beams being scattered around in there. And you have this anti-backscatter backing, which will absorb some of those to improve the definition of the image. Now, this is a kind of negative process. The darkness of the film locally depends on how much radiation hits it. So the more radiation which hits the film, the darker it gets. If you've got a defect there, it creates, it's a void. Let me start again with that. The film darkness varies with the amount of radiation. The thicker areas will absorb more radiation and they will be lighter. So if you've got a weld in a piece of steel, let's say you've got a weld that's got a cap on it and a root on it, it's thicker than the piece of steel either side. And so that will absorb more radiation and be lighter against the background. If you've got a defect, it's a void, and therefore it will be darker. So what's the radiation? Well, the radiation is either X-rays, which are produced by an X-ray generator, or gamma rays, which are produced by radioactive materials. And they're both electromagnetic waves, and they're you can see gamma rays and X-rays on the left-hand side of that spectrum. And you can see the position of where light is, where this is. So it's relative, you can see it relative to UV on there. So they've got short wavelengths and they've got high energy values. So how do you generate X-rays? Well, you generate it with the what is called the Coolidge tube, named after the person who invented it. You've got within that tube, in a vacuum, you've got a cathode and an anode. And the cathode there, you can see it glowing nicely. And the cathode is the negative pole, and it's generating electrons, which are then drawn across to the positive pole. And so they're being accelerated across the gap, and they hit the anode, the positive pole. And that target is made of tungsten, and those electrons striking the tungsten generates the X-rays. Now you'll see that is cut obliquely, the anode that is, and that deflects the X-rays out, and so there's a window there, a glass window, specialized glass. So that creates you've then got the X-ray beam exiting the tube through the window, and then down onto the piece of work. So that's what you can see there is exactly one of these. You've got the tube head, and then there's of course control units and cables and so on, which I don't need to go into in any detail. But you can see the window there through which the X-rays are emitted. And that's a fairly sensitive piece of kit because you've got this glass tube inside, vacuum tube. Now, that's one type of tube. There's another type of tube which gives, so the first one gives you directional X-rays, as you saw on the diagram. But for examining pipelines, then we use a different sort of tube, which creates a panoramic beam. And instead of being that anode being cut obliquely, it is actually conical, and it emits X-rays around 360 degrees. Now, looking at that tube there, which is a panoramic X-ray tube, believe it or not, that black line that you can see there, that is actually the window through which the X-rays emit, and as I say, 360 degrees. Moving on to gamma rays. Gamma rays are emitted by radioactive sources, and they have to be very carefully controlled, and they live in that sort of little lead box, or that rather heavy lead box in the middle there that you see with the yellow handle. So that is where you store your gamma ray source, and it's no use in there for inspection purposes. It has to be at the tip of that thing that's labeled the isotope holder. So you have to wind it out from the container, and that's why you've got that cable with the handle. So basically you wind it, the source, which is very tiny, you wind it out from its lead-lined storage container, you wind it out to the point at the tip of the isotope holder, which is the inspection head. You do your exposure, and then you wind it back in again, back into safely into its container. And the sources used, they might be uranium-238, radium-226, iridium-192, which is very popular, cobalt-60, which is very powerful, ytterbium-169. Those are all the specific isotopes of those elements which are radioactive and used for this. There are others, and of course it's for the radiographer to know what source to use for any particular application. But if it was a very thick material, you might use cobalt-60, which is more powerful than iridium-192, I would say. And there are also sizes of the sources. That's all a bit of that's where the specialist is involved, of course. Okay, so X-rays versus gamma rays. What's the benefit of gamma rays? You don't need an electrical supply. With radiography, with X-rays, you clearly need an electrical supply, and that could be a big limitation. You don't need a cooling system, which you need with an X-ray source. And gamma ray sources can get inside very small spaces. As you saw, it's a fairly fine thing, whereas X-ray tubes are inherently limited in size. There's a limit on on being your ability to miniaturize an X-ray tube. But X-rays generally give greater sensitivity. So there you can see two images. They're not directly comparable, but they're similar sort of pieces. But it's and maybe it's a bit of an over-dramatic comparison, but it does make the point that X-rays give you excellent clarity, and the image you see with the with the use of gamma rays is less contrast, and perhaps less easy, I would say. Gamma rays are less easy to interpret than X-rays. But with gamma rays, there are safety and security issues with both sources. But with gamma rays, there are more issues. For example, transporting gamma rays, there are all kinds of regulations in every different country relating to control of radioactive sources. So more regulation and more permissions are needed if you're using gamma rays than X-rays, because when you switch off an X-ray source, it's not emitting anything. It's not in any way a hazard. So, as I said, the radiograph is a negative image. So we've got a weld there, and because it's thicker, it's absorbed more radiation, and therefore it shows up whiter. And weld defects generally are voids within the weld, and they show darker against the weld line. If you're looking at a radiograph, you would expect to see, and it's not shown on this particular bit of this radiograph, but it should show the weld identity. When you put that radiograph on your viewer, you want to be able to see, you've got to be able to see what its weld identity is. And then you would expect to see an index. So you've got those numbers there. Those are lead letters which have been wrapped around this weld, and they show you the position, obviously. So you use that index, you mark it on your piece of work, and you use that for marking up where the defect actually lies for excavation and repair. So it's all relative to a datum which is marked on the item. And then there's that thing that says 10 FEEN, which is what's called an IQI, an image quality indicator. And in this case, you can't really see it on the image above, but it's a series of wires. You can see what a wire image quality indicator is on the image at the bottom on the left-hand side. And it's a series of wires, and you use those to interpret the sensitivity, how you count which wire you can see, you know the diameter of those wires, and you express it as a percentage sensitivity of the weld thickness. Radiography is excellent for showing volumetric weld defects. Volumetric defects that have got volume to them. But it's not so good at showing things that don't have volume, and cracks and lack of fusion type defects do not have volume unless you're remarkably good at aligning the beam with the crack or the lack of fusion. So, for example, lack of penetration of the weld, and you can see what I mean by lack of penetration there, shows up very nicely as a dark black line. It also is good at showing over penetration or burn through, which would show up much lighter. If you've got slag inclusions, they constitute a void, so they show up as black indications. And porosity shows up well as well. And also undercut. So that's what radiography is really excellent at showing. Just going to talk a little bit about pipeline inspection. We've got there a panoramic crawler unit which goes inside the pipeline, And I've already, in this case, it's the bit between the red bands, which is the window through which the X-rays are emitted. So that's a pipeline crawler unit, and you call that up to, you have a remote control, and you call it up to the center line of the weld that you're inspecting on the pipeline. And there are also panoramic gamma ray crawlers as well. So limitations of radiography. Well, I've already mentioned the safety considerations. They're paramount, both in use and for isotope storage due to the radiation hazard. There's only a radiation hazard with X-rays when the thing is on, but with isotopes, gamma rays, then it's an issue at all times. Another limitation is that radiography provides no information about defect height, and really that is the most important defect dimension in Welds. And radiography is better at detecting volumetric rather than planar defects, as I've already said. But planar defects are much more important, much more likely to be a potential source of failure than the volumetric defects. Now, of course, you are well aware, I'm sure, that film-based methods of radiography are giving way to digital methods. On the left there, we've got the film that's used for pipelines, and that comes as a strip. So that's conventional X-ray film. In the center, what we've got the sort of X-ray plates. Now, those are probably much more like the ones that are used for medical radiography. Nowadays, medical radiography is all digital. And on the right-hand side, we've got the small image showing the makeup of one of those plates. But digital radiography is being used for fabricated items. This is digital radiography for an onshore pipeline. It's a bit of kit from Applus RTD in the Netherlands. You can see it's a hell of a piece of kit, but that's developing technology, shall we say. It is used. What are the benefits of digital radiography? As in general, there's no film, no processing, no chemicals, and you get instantaneous inspection results. The problem with film radiography is that you've got to wait and develop the film and then inspect it, and that takes minutes, and sometimes those minutes are crucial minutes in terms of the progress of the job, particularly in pipeline work. Digital, you get your results instantly. You can interpret them within seconds and call up repairs. Also storage. You can store the results much easier electronically. Film storage is quite a big item in itself, and it requires careful indexing and so on. Of course, you have to. The same principles apply. You have to have a library, an electronic library for digital, but the whole process is easier. There's no equipment in the pipe in this case, and no need for battery changes, which is an issue with inline pipeline inspection. But you can see the equipment's bulky. Okay, I'm going to move on to ultrasonic inspection. That shows traditional UT using modern digital equipment, but just a probe, a weld, an operator scanning backwards and forwards. And I'm going to start by talking about that process of traditional ultrasonic inspection. You can see that the surface has been cleaned adjacent to the weld, and you can also see it's wet. And what it's wet with is sometimes water, but more likely it is going to be a gel of some sort, and that provides the vital function of being a couplant between the probe and the workpiece and giving a continuous path for the ultrasound. So what is an ultrasonic wave? Well, it's a mechanical vibration with a frequency above 0.02 megahertz. And the frequencies generally used in weld and metals inspection are 1 to 10 megahertz. Traditional UT is about 3 to 4 megahertz generally. And what's the principle? What are you doing? You've got a probe there. You're putting the probe on the piece of work, and you've got a couplant, and the arrow for the couplant is in completely the wrong place, which I just spotted. It slipped in preparing this slide for this presentation. I'm sorry about that. That couplant isn't where that arrow shows it to be. That couplant, if you can see my pointer, I can find the actual. I hope you can see the arrow. Pointer options, that's it, the laser pointer. Okay, so the couplant is actually in there in the interface between the probe and the steel plate. Okay. The probe is generating the ultrasound, and what you can see is that it's some of that ultrasound is being deflected, in this case, off the back wall of the plate, and some is being reflected off the discontinuity. So that probe is both transmitting and receiving. And what you've got is what you see on the left-hand side. You've got what's called a time base, which is the path of the beam. And there is an initial pulse that you can see there, which we will ignore for present purposes. But the first blip is the echo from the discontinuity, and the second blip is from the back surface. Now, it follows that if you slide that probe to the left, you're going to just have the back wall echo, and if you slide it to the right, you're going to see the discontinuity. And those peaks will move up and down depending on where that probe is and how much the sound is reflected from the discontinuity or from the back wall. In reality, that probe is emitting a beam which looks something like that, and you can see the intensity and the frequency actually, and the intensity of the beam and the beam path. So the beam path is, the beam itself is quite a complex shape. But think of it as a torch wave. And you've got two types of ultrasonic waves that I'm talking about. There are others, but you've got the longitudinal waves or the compression waves. Now, what we were looking at there is a compression probe, and that's generating compression waves. And there, the waves are vibrating along the direction of the wave. Now, if I had a skipping rope with me, and I gave one end of the skipping rope to you, and I held the other, and then waved my end, a wave would propagate along that skipping rope and would transmit from me to you. And that's what a compression wave is, or a longitudinal wave is. But then you've got shear waves, and that's where the direction of vibration is perpendicular to the line of direction of the beam. And they behave differently, and all the physics and inspection technology accommodates that, takes that into account. And we've got two types of probe then. We've got the compression probes, which you've seen, and then you've got these shear wave probes. And the shear wave probes in traditional manual UT come in 45, 60 degree or 70 degree fixed angle probes. And those are the ones which are widely used in weld inspection because you want to come in from the side, as you saw in that first picture, and you've got your beam and you're moving it around to look at the weld. So compression waves, they're used for thickness checks and for corrosion loss measurements and things like that. You might use them to check that the steel isn't laminated before you start the main inspection with the angle beams, which are used, as I say, for the weld inspection. Now those probes, they've got a known frequency, they've got a known angle of entry and a known beam width. And the whole principle is what you've just seen, that the defects in the joint, they interrupt the sound, they give a reflected beam, which is detected, and it comes back to the probe, because we're talking about probes which transmit and receive. It comes back to the probe, and that's displayed on the screen that you saw in the images, in the previous images. Now, in reality, probes can either transmit, receive, or do both. But for weld inspection, traditional weld inspection, you're talking about being transmit and receive. So that's it again. You've got a probe there, you've got a weld there, and the probe is being pushed. That probe has got an index, which you can see in the clearly marked. That vertical line on the side of that probe is where the center of that beam exits that block. That's just a transmission block, as it were, to get the beam out at the fixed angle. And then you've got the couplant on the plate, which provides continuity for the beam. I'm not going to go into this in a great deal of detail, but anybody doing manual UT will come armed with all their calibration blocks, and that is to verify, first of all, the equipment and the probe characteristics, is to set the sensitivity of the inspection in accordance with the code that's being worked to, and it's to develop something called, or a set of blocks are used to develop the distance amplitude correction curve. So what's that about? Well, if you think about a torch beam, again, of course, the amount of light that is received and comes back from anything you're looking at with a torch decreases in accordance with the inverse square law. So things further away give a less light, less reflected light than things close to you. Something you all understand, know. And the same thing happens with UT signals. So that has to be taken into account, and that's done by constructing this thing called the distance to amplitude correction curve, to take account of the decrease in signal amplitude with the distance from the probe. Now the x-axis on that screen there is distance. It's calibrated to mean distance. What you've got is you've got the 1, 2, 3 there, and that is the signal that you get back from calibration holes in a calibration block, which are all the same size. And as you're further away, they reflect less ultrasound back. So you have to plot a curve to show that, so that you know what you're getting back and where your defect lies. And you do this calibration with holes in a calibration block, and they're fixed, as it shows in the picture, at the quarter, half, and 3/4 positions of the material thickness, and used to construct that distance amplitude correction curve. And that's one being plotted in real time, as it were. That's a real DAC, and they've plotted a number of points there to produce a DAC. And that curve would come right down to the bottom. It's in process of being prepared. Practical aspects of UT. Well, again, think about your torch beam and think about the orientation of weld defects, where weld defects will lie. And you can understand that your torch beam or your UT beam will miss defects or will show them at different amplitudes, depending on their position. So the principle is that you should scan from all accessible surfaces to detect all defects. And those images there give you an idea of what the scanning, how you would set about trying to detect particular types of defects based on their position relative to the weld and the joint configuration. And the choice of angle probe used, bearing in mind we've only got 45, 60 and 70, the choice of angle probe is another thing here, another consideration here, and there are some guidelines. But generally, when you're looking at Welds, you're going to be using 60 and 70 degree probes. In fact, all of them, depending on the situation. There will be a procedure written that will cover the joint configuration and so on. So it's not left to chance. And how do you indicate? How do you interpret and report your indications? Well, in ultrasonics, you generally report them as whether they're planar defects or volumetric defects. You look at their length or their accumulated length. You look at the amplitude of the reflected signal. And there is a requirement in some codes and standards to try and interpret the type of defect. For example, if you look at the American Society of Mechanical Engineers NDT code on Article 9-3, cracks, lack of fusion, or incomplete penetration are unacceptable regardless of length. That's the requirement if you're working to that standard. So the operator has to have the ability to interpret the defects, and that's a lecture in itself. So what are the strengths and weaknesses of UT? The strengths are that it finds the critical defects. It can find the critical defects, which are the planar defects, cracks, and lack of fusion. It's a very flexible process, obviously. What are the weaknesses? It requires highly skilled technicians to do it. A lot of training is involved with those guys. They also need to know something about welds and a bit of an understanding about welding technology in order to be able to do the interpretation. It can be very slow, and if you've got a lot of defects or if there's some debate about whether something is acceptable or not, it can be very slow indeed. It's subject to a lot of interpretation, and that causes some issues, can cause issues if there are various people watching the UT man at work and saying, well, I don't agree that that's a benign defect, a benign indication. And the signal amplitude, what you see back, how high that, although you've plotted that nice distance amplitude correction curve, the amplitude of the signal you get back doesn't exactly correlate with the size or the criticality of the defect. And traditionally, the reporting was paper-based or somebody filling in a report sheet. Things are changing. I'll talk about a couple of developments. Development one is that phased array technology is replacing fixed angle probes. And these, although they look superficially similar, there's a phased array probe there, superficially might look similar to the other probes, but they're completely different in that they've got many elements from 16 to 256. So that probe there's got 16 elements, it says there. And one probe is equivalent to many fixed angle probes. And what this reduces is the need for pushing that probe backwards and forwards to find the defect, because, well, that's a UT set up for phased array, and it's setting out this, it's showing this wide beam, which is an accumulation of many signals from many channels and probes, which kind of gives you a live view of the indications, a simulated view. So what's the advantage of this? Another advantage of this modern technology is that it gives you full recording of the scans and images, so you can go back and reinterpret or look very carefully at the interpretation of what you've got. So what is phased array? And you've got many elements, but what you're doing is in phased array you can generate many different types of probe, normal beams, angle beams. You can also produce things that are called focused or unfocused beams. You can produce shear waves, longitudinal waves. You can really play tunes on it. which puts a whole new dimension to the skill of the UT, the people setting up the UT engineers. So what you've got there, this is just a simple representation of what's happening. You've got, it shows 5 elements there, and they are firing at different. There's a firing at different times, milliseconds apart, and they generate a different sort of wavefront, and you can vary that wavefront by the way that these channels are fired. And what you're doing is, in reality, is that you've got your phased array probe, and it's producing a sectoral scan, and it's equivalent to many angles, many different angles. So it's giving this broad beam approach into the world. Well, as you can see there, all done simultaneously without pushing things backwards and forwards or changing your probe type. And you get the image, and you get a live image showing the indications. Now, that's not without its interpretation challenges, but I think it's much more intuitive as to what you're seeing. Not always a good thing, but that's the case. So that's phased array technology for you. And then another development is time of flight diffraction ultrasonics. Now, it's also ultrasonics, but it's very different indeed. It has the benefit that it can actually size indications very precisely, or with interpretation can be used to size indications very precisely. That's a better way of putting it. And it was developed for the nuclear industry at Harwell, originally at Harwell Laboratories in the UK. It's gone a long way since then. Okay, so let me try and explain this image to you. Let's start with what you see at the top. 2 probes at a fixed distance apart, a known fixed distance apart. One is transmitting, the other is receiving. And you've got a lateral wave which is propagating immediately subsurface between those 2 probes. And then you've got another wave which is giving you, which is an angle wave, shear wave, and it's hitting the back wall. It's giving you the back wall reflection. And then, if you've got an indication, you've got these other waves, these other angles, which are finding the tip of the defect. And what you're doing is you're getting diffraction. They are acting as little sources of their own, setting off other waves that go in all directions, but some of those get to the receiver, and the receiver can see those and they are shown as the upper tip and the lower tip of the indication. As I say, as I should have said, those 2 probes are entirely symmetrical to the Welds center line. So it's only applicable, only possible to do this with butt-weld geometries. So now we look at that. This is what you're seeing on the screen. You're seeing the lateral wave, the green wave in the other image, and you're seeing the back wall echo. They're clearly visible, and defects show up between the 2 as the diffraction signals. I'll just try and give you a simulation of that. So that diagram there is familiar on the upper left, but you've got the lateral wave and you've got the back wall echo showing. So you've got the length of the weld now. What you're seeing on the bottom is the length of the weld, and you've got the lateral wave and the back wall echo, and the peaks and the troughs. The black and the white correspond to the peaks and the troughs. So you move those probes and you get that. So you've got the lateral back wall. Now let's introduce a defect. Hope this works. Press again. Yep, we've got our defect there. So now that's giving you the diffraction signals. So now they come up there. So you can see the length, but you can also see the an indication of height. It's not a direct measurement. It requires calibration skill and knowledge to interpret the height dimension. I'm just going to go back. I'm just going to show you a short video of automatic ultrasonic inspection of pipelines. I don't know if you can hear me over the top of this, but what they're doing is they're calibrating the equipment. Oh, I'm sorry, I didn't mean to do that. I was just turning off. So that's a piece of UT equipment, and they've just calibrated it on the calibration block, and they do that for every weld. That thing that they've got there is a band that they put on the pipe. Sugar. So now putting a band adjacent to the girth weld that they're going to inspect. I'm sorry about this. Can't keep the. I'll let it just run and I'll explain it afterwards. So they're marking the datum. They're aligning the band very precisely within a couple of millimeters. The tolerance on that is just a few millimeters. Now they're taking the UT equipment. Bringing it up to the top dead center. All clear, everything ready. And now that will traverse around the pipe pretty quickly. And then in the van there, the interpreter is seeing the indications that are coming up. So it does the 360 degrees. You can see the couplant on there. And there you can see lots of channels there on the trace, which is called a strip chart. And some things came up in red and green there, which are indications. So that's it. That's that weld finished. Then they're marking what they've done and what the findings were. So what have we got there? We've got the UT head, which travels circumferentially around the pipe weld. And that head has got basically two probes in it, which you can see as the rectangles in the bottom image there. But those are phased array probes. In fact, they can also generate time flight diffraction signals as well. So they're very, very sophisticated probes there. There's an encoder so that relative to the datum, that strip chart, the reporting knows exactly where around the circumference it is where any indications originate. And it scans up to 150 millimeters per second, so very fast inspection technique. So they're phased array probes, and what you're doing is that you're looking at the full thickness of that weld, but it's very clever. That weld is divided up into a series of bands, and those channels, well, I'll come to the channels in a minute, but you've divided the weld up into different zones, and the probes are actually focusing on each of those levels. So there's a different channel for each of those levels that you can see there, the zones. And they're, as it says there, between 1 and 3 millimeters in height. So the ultrasonic transducers, they're generating signals which are focused at the optimum angle for each zone. So you get a zone discrimination, so you know where any indication originates. So a signal detected on one transducer comes from that defect. There's a little bit of an overlap, which the operator knows all about and can interpret. And you need to go into calibration. That's what the calibration block is. It's a very sophisticated thing, is that calibration block with lots of reference reflectors. I don't have time to talk about that more at this moment, but there are reflectors for each zone. And then you get the strip chart, and this is just one half of the strip chart. And what you've got is you've got these zones, and those zones are marked at the top there, and they correspond to the zones that you saw on the weld diagram. And then you've got a couple of what are called, we've got 3 mapping channels where you can see you get an interpretation there, but in the center you can see, or well, on the left in this case, but what is actually on the center of the full strip chart is the time of flight diffraction channel that I've already mentioned to you. Now this is a calibration block, and it's picking up the indications from the signal, the defects in the calibration block for that zone, which is why it's red. And I'm sorry, the strip chart corresponds to the circumference of the pipe. So that's a length dimension as you run down. So each strip corresponds to a different inspection zone, and you've got the TOF channel. And you can, from that, the interpreter can see the height, size, depth, length, and position of any indication relative to the weld center line and the weld bevel. So it gets a lot of information from that trace. So it's a very, very clever system. So I'm moving on, and I'm moving on to acceptance criteria. Non-destructive testing codes, you will find that a lot of the codes just are there to standardize the test method, making it quite clear how you do it. In the case of dye-penetrant inspection, for example, how long you let it stand with the dye on it before you clean it off. It's a simple example. What I mean is, most testing standards or codes don't state the acceptance criteria for the defects. They are methods. Standardize the method, standardize the calibration and the procedure. The acceptance criteria differ based on the application, and there is a wealth of codes for welded structures, for pipelines, for nuclear applications, for pressure vessels, and so on, which you as welding engineers may have come across. And it's there that you normally find the acceptance criteria, that you're allowed a planar defect of a certain height, a certain length, a certain location relative to the cap or the root. So you have to refer to the specific application code, and the criteria do differ. For example, I'm comparing 2 standards here for incomplete root penetration, and API 1104, which is a pipeline standard, allows 25 millimeters of incomplete root penetration in 300 millimeters of weld. whereas ISO 5817 level B states that incomplete root penetration is not permitted. Now, why have we got these differences? Well, it's because two things. One is it depends on the application. If you're doing nuclear work, it's very different from doing standard pipe work or a structural weld for a canopy of a building or something like that. And the acceptance standards are also workmanship based. It's what's considered good practice. It's what was decided and discussed in the code writing committee. So there is incredible variability, and it's very important for welding engineers to know exactly the application, have the specifications very clear in their mind, and have that set in their working procedures. I'm just putting up a few standards. In fact, the British standards, and very often they're BS-EN, which is Euronorm, European, ISO, international standards. But for the different methods, there are these BS-EN ISO standards that define the test method. So running through that, for example, we've got looking at MPI, we've got part one of that standard is general principles, and then we've got another standard that's a different number. Sometimes you find there are multiple parts, sometimes you find they're different standards. So we've got three there. We've got general principles, we've got the execution of testing, and then we've got the acceptance levels, and that the acceptance levels in that standard will depend on the application. Different acceptance levels you'll find. Probably three different sets of acceptance levels. The same with penetrant testing. I mentioned eddy current testing, but the same with eddy current testing. And then radiography, a whole range of applicable standards there for different materials, different techniques. So you can see mention of steel, nickel, titanium, aluminium. You can see phased array technology, standard for phased array technology. And you can see the difference between film and digital. So all of these things have been standardized, and obviously you must be aware of what standard you're expected to work to. The same with ultrasonic testing. We've got general principles, we've got the techniques, we've got the sizing methods, characterization. I said that in some standards you have to be able to distinguish what type of defect it is. It's not easy with ultrasonics, and so you've got characterization there, the techniques that are used for that, and then acceptance levels, and then different acceptance criteria for austenitic stainless steels, for time of flight diffraction. So a lot of different requirements based on the method and the application. And then general standards on quality levels. Just looking for what I possibly should need to pick out, what I need to pick out for you there. If you look at 5817, that's got, and that's the one for steel, and the other materials listed there, but there are different quality levels depending on the application. And then we come to qualification of personnel, which is a very big area. Personnel have to be qualified, and these standards set the basis for qualification of NDT operators and inspectors. That, I think, is the end of my presentation. So I'll stop sharing and hopefully take some questions.
Excellent. Thank you very much. Thanks very much, Alan. It's very helpful. Yes, we've got a couple of questions. I'll just take myself off screen and just so you can answer them. And if you feel the need to reshare again, please go ahead. I've tried to organize them by technique. So they're not in the order that's been given. So starting with MPI, the first question is, can you please advise how to confirm if the magnetic field strength is adequate? Now, I remember your slides kind of mentioned the figure of 30 to 50 Hz. That's me speaking. But maybe can you elaborate on if you've got any more light to shed on this? How do you confirm that the field strength is adequate?
Yes. Okay. Well, I mean, the first thing is the calibration, and that was the weight. You know, the magnet has to be able to lift a weight, and that weight is defined in the individual standard that you're working to. It varies quite widely, but that's just indicating the power of the magnet. In terms of field strength, there are field strength indicators, which are small devices, which are just little coupons which go on the work. With a number of engraved lines, and you've got to be able to detect those. So you can use one of those, and you've got to meet the appropriate. You've got to be able to show those indications that are on that field strength indicator. So that's something else, and you'll find if you're going to use, you'll find the requirements for that in the code or standard that you're working to.
Great, thank you. The next one, also on MPI. Can MPI detect subsurface defects provided they're close enough to the surface, or very close to the surface and large enough?
I've never trusted it for doing so, but if you look at the literature, it would tell you that it can detect immediately subsurface defects.
Okay, yeah, good. Moving on to LPI, on what basis could you choose between red dye or fluorescent dye to detect surface defects? Is there one that's more sensitive than the other?
I wouldn't say so. I think it depends on the culture of the organization and where they're working. Certainly, I've seen in shipyards, for example, a preference to use if you're inside the covered fabrication shops, I've seen a preference for using fluorescent because of the light conditions there, and you can detect things much better. Certainly in a workshop environment, I've seen fluorescent used simply because it suits the lighting conditions, the working environment, but also their setup in terms of if you're looking at shafts and things like that, they've got sort of fixed booths where they would slot the shaft in, they do the inspection, or bolt inspection. I've seen kind of fixed equipment that works with fluorescent materials, because that's what they've chosen. But it's horses for courses, I think.
Yeah, okay. No, that helps. On the same topic of LPI, is there any way to estimate the crack depth depending on the level of bleed out you get?
No.
Okay. Yeah. Good.
I mean, people say, yeah, you will get people saying, "Oh, that's not much." You'll get a kind of maybe a very, very light indication, and people might say, "Oh, there's not much there," and they'd be right.
Okay.
And then maybe you'd dress off the weld in that area, dress off where that indication is, and then you'd repeat it, and it might disappear. So yeah, but only on the crudest of levels. If you just see something really superficial, you might do that, but otherwise, no.
Yeah, no, excellent. Thanks, Alan. There's on the topic of subsurface defects. There's a follow-up question. Is there a minimum indication size that either MPI or LPI can detect subsurface, and can you quantify that by depth?
Well, LPI won't detect anything that isn't actually surface breaking. MPI is said to be able to detect things that are immediately subsurface. Just repeat the question though, Mark.
It's if there is a minimum indication size that they can detect in general, but then for subsurface, is it quantifiable by depth? You've already kind of said no. Well, LPI needs to actually be able to get into the defect to find it. So it's maybe more applicable for MPI then.
Minimum depth, minimum. You get. I mean, the reality is you're dealing with. You get quite a lot of suspect indications, which are not real defects. I can't, if you're talking about things of 0.5 millimeter, less than 0.5 millimeter, you might be picking them up, and you'd have to go through a process of being prepared to clean up, maybe dress locally, and so on. I can't answer the question directly, to be honest, Mark.
Yeah. No, let's move on. Moving on to radiography now. What's the thickness suitable for kind of use for either X-ray or gamma ray? Can it be thickness dependent of your sample?
It's a bit of yes and no. You choose your the power of your X-ray set, or the isotope. The isotope you're going to use based on the thickness of the material. So it works the other way. You start by looking at how thick it is, and then deciding how you're going to inspect it and what you're going to use to do it. You can inspect things of considerable thickness if you use the right gamma ray source or the right X-ray source. But obviously you run out of steam at some point. It's much easier to examine things that are 10 to 50 millimeters thick than things that are 100 to 200 millimeters thick. You run out of options very quickly when you get very, very thick indeed. But this is all really for a specialist to advise you. A real specialist in NDT. This is an introductory lecture for general awareness, and I think there are other people who could possibly answer that question better than me.
Excellent. The next couple of questions also on radiography, I think maybe more introductory. Can you use radiographic testing for dissimilar welds?
Yes.
Yes.
Yes, you can, and it is.
Digital.
And it's easier than with ultrasonics, because it gets very complicated to apply ultrasonics to dissimilar welds, but you can apply radiography. Yeah.
Excellent. Digital radiography. I think it's another easy one. It still uses conventional radioactivity sources like X-rays or gamma rays. Is that correct?
Yes, the sources are the same.
Are the same. Excellent. Thank you. Right, moving on to ultrasonics now. Can you advise what type of probe to use depending on the different type of materials? For example, carbon steel, duplex, stainless, etc. Are the probes material dependent?
Well, can I advise? No. Can a specialist advise who is you? Look, most of the time people are dealing with carbon steel, in my experience. When you get into inspection of duplex stainless steels or mixed or even carbon steel to austenitic stainless steel, you're into a very specialized area. You need people who are much more specialized than I am to be able to advise you. Is the point? Yeah.
Excellent, thank you. Next, still on UT, how do you take into account background noise when you're using ultrasonics?
Background noise.
Yes.
I've got to think how to answer this. If you're doing UT with carbon steel, you just do it in accordance with a procedure, a standard, and the material, you follow that, you shouldn't have an issue with background noise. If you're looking at austenitic stainless steels or duplex stainless steels or nickel alloys, other alloy types, then interference, beam scattering becomes a very big issue. But again, this is going into the realms of the specialist and specialist NDT companies, and you need those people to advise you, and you're going to have to find the person who really knows that material and that has developed the techniques for looking at that material. It's a pretty specialized area. The core expertise is for carbon steels, and most people are trained for those. You will find people who've worked in UT all their lives and they've done nothing but look at carbon steel. If you're getting into stainless steels and nickel alloys and so on, then you're in the land of the specialists.
Excellent, thank you. Next question is, how do you decide what material thickness is considered thin or thick for the choice of probe angle in UT?
Well, there's some generalizations on the slide there, I recall. It comes down to the knowledge and skill of the operator, but the operator will probably be working in accordance with time-established procedures within their organization, which would determine this. Setting up the UT procedure, and that's something I haven't mentioned at all because this is really just an introductory lecture. Setting all of that up for the material can be quite a time-consuming process, but the operator or the company would have established procedures for the material thickness, the joint configuration, and the standard they're working to. And those procedures, they've been laboratory established before they go to the job, and then they are simply applying those procedures in the field. They check the calibration, but then they go out there and they're working to a certain procedure. I'm sorry, it's not a precise answer, I know, but that's the best I can do for the moment. Because it's a specific question, really, specific to the application, and it's all developed for that application.
No, but it gives us a good direction. Thank you, Alan. And I suppose there's a few questions that are coming through now about UT, but I think we're going to save these for the post-event Q&A. We do have a couple more kind of general ones. So for dense materials, something like nickel or tungsten with small cracks, which technique do you think is most suitable for detection?
I think you're, yeah. I think you're probably in the field of radiography. I think somebody will come up with ultrasonic techniques and be able to advise you on the ultrasonics, but they would be very, very specific. You'd start with radiography, really, if you're looking at volumetric inspection. And if you're looking at surface inspection, then you're looking at dye penetrant, really.
Yeah. Excellent, thank you. And maybe a couple of last questions on standards. So you've mentioned that some of the standards providing acceptance criteria, API 1104, ISO 5817, someone's asking for more. And I assume you had some in your slides, but he's asking just for more, if there are any more prominent ones to be aware of.
Well, there was some on the list there that set up acceptance. Look, this is in the field of almost encyclopedic type questions, and I mean, if you're working in pipelines, a lot of people work to the DNV standards, Stepnoska Veritas standard, or certainly offshore pipelines. They work to those standards, codes and standards. If you're looking at pressure vessels, then a lot of people will look to the ASME code, boiler and pressure vessel standard. And then if you're looking at the EN standards, then I refer you to the tables in the presentation, but also page 31 of Welding and Joining Matters, issue 11, which has got a list of BSEN standards. But my God, we're talking, there are hundreds of standards. And then when you get into it, you find that all your clients have got their own overlay on the internationally recognizable standards. So it's a very tricky area, this, but I could spend a lot of time. Well, in the journal, we try and compile these things because we know it's a can of worms, and we try and provide people with the information that they can go back to. That's the whole point of the journal, which is to have articles of record there that people can use for reference later, that will hopefully be able to cover some of these encyclopedic issues. If people want, well, some of these questions I think probably would be better turned into journal articles. The replies to them could be better done as journal articles.
But no, understood. That's great. Alan, thank you
I'm
very much.
just trying to give you a taste of the subject here.
Yes.
That's the purpose.
Yes. No, and it was very, very insightful. Thank you very much. I will just share my final couple of slides and pop them on the screen. So yeah, thank you everyone for attending. It's been a great webinar. I've personally taken away a lot of it. Please, we will circulate your questions to Alan, and we'll share the recording afterwards and the slides as well. If Alan gives us permission, you'll get the CPD certificates by email, but please do give us feedback. It's your feedback that really makes these webinars what they are. So we're going to post a link in the chat. Please feel free to go in and tell us what you thought and what we could do to make it a better one next time. And then if you'd like to get more involved with the TWI, I've left some membership details here on the left. You can reach out to them by email or go on the website or even a call. There's all these benefits to joining the TWI on screen as well for your review. But again, thank you very much. We've enjoyed hosting you, and have a lovely rest of the day.
Thank you. Thanks for attending, everybody.
Thanks, Alan. Thank you.
Mark, maybe we can have a debrief afterwards.
Yes,
yeah?
I will end the event now. Actually, I'll give people a chance to just click on that link.
Okay, Mark, I'm going to close the meeting now.
Thanks.